A concurrent program is one that can be broken up into logical pieces, and those pieces can be executed simultaneously, usually on different processors and sometimes on totally different machines. Now, the breakdown of program may be by functionality. In other words, one concurrent piece may be recognizing keystrokes from a word processor, and another may be doing a backup of the document to the disk. Or the breakdown of program functionality might be by data. So a large array of data might be broken into different pieces, and different processors will process the different chunks. In the old days of at least PC applications, and by old days I mean just a few years ago, we didn't have a whole lot to think about. We knew that our programs were going to be running on the one and only processor in the computer. But now the landscape has really changed. We're about to enter a world where there'll be more and more processors on the computers that our programs run on. So my first cell phone, for example, had one processor for the applications. The last phone I had 2 processors. My current phone has 4. Okay, you can probably see where we're headed. Okay, if you look at these, the history of your phones and the number of processors in them. In order to take advantage of this, we need to know how to write concurrent programs. Now, this is actually a really big topic. We're only really going to be scratching the surface here. Okay, let's start by talking about state. So, the state of a variable represents its value at a certain point in time, and time is important here. So the roster of the Carthage baseball team, for example, is different than it was 4 years ago. The old roster is a value at a point in time. The current roster is another value at the current point in time. Both represent the same thing, the identity of a baseball team. In 4 years there's going to be an entirely different roster, but that should not necessarily affect the values of the old ones. In Clojure, since our data is immutable, we're constantly storing values at different points in time, and these values can never change. In most programming languages, when we write a value to a variable, the old value is gone forever. We lose the value at a specific time combination. Since data is immutable in Clojure, we simply can't write over an existing variable. We can choose to not remember an old value if it's not important to us, but we can't wipe it out in favor of a newer value. So if we do choose to not remember that piece of data, it will be garbage collected by the Java virtual machine. Some people would argue that the ability to change the state of a piece of data, that is to have mutable data, introduces a lot of complexity. So think of the point and line example I talked about in one of the earlier video lectures, where calling one function like line.move introduces an explosion of state changes in all the point objects. If there are 2 or more processors working on that line at exactly the same time, this can be really difficult to deal with. Sometimes, however, we do need to share state between different parts of a program. There are certain scenarios where there's just no easy way around it. And in a functional programming language like Clojure, it's best to limit and isolate these cases. So let's kind of look at an example of why. Okay, so let's pretend this isn't necessarily a program, but let's pretend both me and my wife walk up to ATMs, 2 different ATMs, at exactly the same time, and we both want to withdraw $100 from our shared bank account. So we have $500 in this shared account, and the question is, well, what's going to happen if we both walk up to these ATMs at exactly the same time and try and withdraw $100? Now, of course, what we're supposed to be doing here, or what the bank is supposed to be doing, is taking the value 500 and subtracting the $100 we want to withdraw. So after I withdraw, there should be 400, and after my wife withdraws, there should be $300. So, that's kind of the question. What is the balance after the withdrawals? Is it $300? I would certainly hope so. I know the bank would want that to be true. But I can tell you from experience, if you're doing some kind of program that does a similar thing, you might end up with a balance of 400, depending on when the transaction completes. Okay, so just try and imagine that we walk up and hit our buttons at exactly the same time, and when we go to withdraw the $100 or subtract that from our account, if things lined up correctly where these things happened at exactly the same time, we could say 500 minus 100 is 400, put that in here, but at the same time 500 minus 100 is 400 here, and instead of having 300 we only have 400. So how might we solve this problem? Well, we could have someone guarding the each account. So we could have, let's say, one bank ledger with every account in it that's guarded by a bank employee. And anyone who wants to change the balance of an account must coordinate with that bank employee. So now no two people can change the ledger at the same time. Right? So now if I walked up to ATM 1 and my wife walked up to ATM 2 at exactly the same time, well, we'd have to get in line. We'd have to get in a queue, and only one of us could withdraw the $100 at a time. This will solve our problem. But at the same time, it introduces some other problems. If there are hundreds or thousands of accounts in the ledger, the one bank employee is going to be a bottleneck. Okay, updates will not happen in a timely manner. So to solve this problem, we might have a bank employee for each account in the ledger. Again, making sure that when one person is updating the account, no one else can use it. If there are two or more people who just want to read the balance, though, they really shouldn't be locked out or prevented from doing so. But in this scenario, they are. Okay, so it turns out there should be different rules for people who are reading data versus people who are writing to the data. Now, many programming languages deal with this by locking sections of code so that only one part of a concurrent program can access a critical section of code that refers to some shared state at a time. But this is very tricky business. It's easy to think that your code is correct and protected, only to find out later that the program is incorrect. Okay. That's one of the really hard parts about developing concurrent programs. Is it's kind of hard to recreate the scenarios when something goes wrong. Now, Clojure provides some constructs that allow concurrent access, kind of like with our bank employee here, that are very simple and pretty hard to screw up, which is good for us programmers. When you must share mutable data, you'll use this thing called a ref and a transaction, or this thing called an agent. Okay, so let's look at these. A ref is a reference to a piece of data that can change. So think of it as a pointer that can point to different immutable data at different times. Okay, so a ref wraps and protects access to a piece of data. And basically the way we create a ref is we use a function called ref, and then we give an initial state for the piece of data. Okay, so here's some code where I'm going to create a ref that points to a string that has the song title Happy. Okay, so I'm creating a def. It's called current track. Okay, and here I'm calling the ref function to create my reference to the string called Happy. Now we can think of this kind of like a pointer or reference. We want to dereference that piece of data. We can do that with the deref function. So now when I print, I should say the current track is happy. And then there's a shorthand to do a deref. That's the @ sign here. Okay, so we should see current track happy twice on the screen. Now in order to change a ref, you need to use this function called refset, and then wrap the code inside this thing called a transaction. and we'll talk about transactions in a second. The doSync function creates the transaction for us. Okay, so this is similar code. We have the current track. It points to a ref with this song title in it. I can dereference it to print it out. But now if I want to change it, I have to use a transaction, and then inside the transaction I have to call the refset function, and I have to say I want to change the thing called current track equal to this song. Okay. And then if I print out the current track, we should see that it has changed. Okay, Clojure uses this thing called software transactional memory, or STM, which is similar to how transactions in a database management system work. So I said the doSync creates this thing called a transaction. Let's talk a little bit more about what that actually means. So all blocks of code wrapped inside a doSync have the following properties. They are atomic, consistent, and isolated. Okay, what do each one of these words mean? Well, when we say atomic, what that means is outside of the transaction, the entire block of code inside a doSync will appear to happen in a single atomic step. Now this is an illusion, of course. We can't do multiple things in just one step. But to the outside world, it appears as if all of the statements inside that doSync happen at once. And the final results are hidden until we know for sure that that transaction will complete. Transactions are also consistent, which means if anything bad happens inside a transaction, like let's say an exception is thrown, the data is rolled back to its original state. The transaction will never have half of the updates completed and half uncompleted. Okay. Either all of them succeed or all of them fail and the data is rolled back. We never have this halfway. Okay, all transactions are isolated, so no one outside of the transaction will ever see partial results of the actions inside a doSync. The results are only made available after the transaction succeeds. Now, databases have an additional property called durability that ensure if the power goes out during a transaction, the data can be rolled back after the machine starts again. And this is accomplished by only writing the final results to the disk. Okay, so since all the things we're talking about in Clojure happen in memory, we don't get that guarantee. We don't get the durability guarantee. We get ACI, not ACID. Okay. And in databases, we call databases, they have these ACID properties. Okay, so we don't quite have all the ACID properties, but we have most of them. Okay, so refset changes what the ref refers to. Sometimes we just want to update a ref based on its current value. In other words, we don't want to replace a value altogether, but we want to append or remove a value from a list. And this is where the alter function comes in handy. Okay, so here I'm creating a def called names, and I'm creating a ref which is referring to right now just an empty list. Okay, so if I want to alter the list, I want to add something to it. Again, I have to wrap that code inside a transaction using doSync. Okay, and this has the ACI properties that we just talked about. All the code inside here is atomic, consistent, and isolated. Okay, but then we call the alter function. We say we want to alter the thing called names, and then we pass in the name of a function that we want to call, and then the value that we want to pass into the function. Okay, so this basically turns into a call to conjoin the thing called names. We want to add the value mark. Okay, so then I print the names by dereferencing it. Then I do a few more alters, and you should see that the list really is growing. We are able to add all of these items to the list. Updating refs is a synchronous activity, meaning that the flow of control does not continue until the update has completed, until that transaction is completed. You can also update shared state asynchronously using this thing called an agent. Okay, so this looks a little bit similar. We have a def for this thing called counter, and we're creating an agent with an initial value of 0. Okay, we can dereference an agent just like we dereferenced a ref. Okay, so this should print out the initial value. Okay, the way we work with, or the way we alter agents, though, is we use the send function. Okay, so what this says is we want to send into the agent called counter the function inc to increment the value. And what this does is it puts that function on a queue. Okay, and at some point in the future, all of the functions in this queue will be executed and will work on that particular piece of data. Okay, so if we run this, we should see that the initial value was 0. Okay, but then we sent the counter this function called inc. Okay, inc got put on this queue, and eventually inc was applied to counter. Okay, so it went from the value 0 to 1, and then when we dereferenced it, we now see the value 1. Okay, so the send function queues up functions to be called on the agent, and they'll be called at some point in the future. The important part to realize here is that the flow of control returns immediately from the send call. Okay, so as soon as we add that inc function to the queue, the flow of control picks up right here, and we continue on. So the flow of control returns immediately from the send call, but the passed-in function may not be called until later. And this is kind of the definition of an asynchronous function call. So we can visualize this by saying every agent has a queue associated with it, and when somebody calls send, the functions are just going to be put in this queue, and then as processing time permits, the counter, these functions are going to be applied to the agent, and in this case, we updated the values by incrementing it by 1. Okay, let's look at another program that uses an agent. Okay, so I want to prove to you that the function calls actually get queued, and they might be run, or they definitely will be run at some later point. Okay, so I'm going to write my own inc function. I call it slow inc. So remember that the built-in inc function just increases a integer by 1. It's exactly what I'm going to do, but I'm going to add this this thread.sleep for 1,000 milliseconds, or basically 1 second. Okay, so what that means is when somebody calls slow inc, we are going to call inc and increment that value, but before we do that, we're going to wait a second. Okay, so that's slow inc. Okay, I create my counter, which is an agent which has an initial value of 0. I'm going to print that initial value, and then 3 times I'm going to call the send function. Okay, I'm sending to the counter agent the slow inc function, which takes us basically a second to increase a value. Then what I'm going to do is I'm going to print out counter right away. Okay. And what I'm expecting to see here is that the value is probably going to be 0, because even though we've sent the 3 function calls, each one takes a full second to complete, and the flow of control is going to pick up immediately after we queue up the slow inc function. So I'm expecting to see counter equal to 0 here. That was the initial print. Counter equal to 0 here, because even though we've queued up these functions, they haven't been executed. Then I'm going to cheat a little, and I'm going to sleep for 3,000 milliseconds, 3 seconds basically. And then I'm going to print out the counter value again. And here's where I expect to see the full value of 3 for that counter. It does take 3 seconds to finish, and then here we have counter equal to 3. So again, the first print was before I called send. I called send 3 times and printed again immediately. The fact that this has a value of 0 should prove to you that this really is an asynchronous call. The flow of control returned immediately and just picked up here. Then it printed out this. Then we slept for 3 seconds, and by the time those 3 seconds were over, each one of the calls to slow ink was complete, and then we get the value 3 here for the last print. Okay, if you can't continue unless all of the updates in a transaction are completed, then you should definitely use a ref and not an agent. However, you can do other work after you send the agent some work, and then wait for the asynchronous work to be completed using the await function. Okay, so this might happen if you'd like to get the ball rolling on one computation, do a little more work on another, but then at some point in the future, just kind of wait for that original operation to complete. So here's a slightly different version of the slow ink program. Okay, we have slow ink, we have our counter, we have these calls to send. Okay. But then what I'm kind of simulating here is, let's do some other work here while we're waiting for those 3 slow inks to complete. So we could do stuff here. We could still make some progress in some other part of the program, and then wait until this particular agent's queue is empty. In other words, all the slow inks have completed. And that's exactly what the await function does. It blocks the main program until all of those sends have completed. Okay, so now I don't have to put that thread.sleep for 3,000 milliseconds in there. So now we can just wait until all of them are complete. And at this point, we should know for sure that that queue is empty. We've called slow ink for those 3 times. When that happens, when the queue empties, the flow of control is going to pick back up right here. We're going to awake, basically. And then we are going to print out the counter value, which should be 3. Okay, so we did print the initial value of 0. Then it took some amount of time to execute the slow ink functions. And then finally we print out the value 3 without having to guess with a thread.sleep. Now Java has the ability to spawn new threads of execution in a program. And since it's part of Java, we can use it in Clojure. So here's a program that creates a couple threads and starts these threads and executes them. So the way this works in Clojure is you write functions. I have one called run hello and one called run world. And then we can create a thread using the new keyword. Okay, so we want a new thread, and then we pass in the name of a function. Now a new thread is going to be created, and the flow of control for that thread is going to start inside whatever function you pass in as a parameter. So this creates a hello thread and a world thread. Okay, but when you create a thread, nothing really happens until you start the thread. So this is how I'm starting the hello thread and the world thread. And if I run this, we should see hopefully hello world on the screen. Okay, which we do. Now it is entirely possible that the world thread, the one that we started second, could be scheduled to run first, and that would be awkward, right? Because usually we see hello world, not world hello. So we, the programmer, have no direct control over the Java virtual machine or your operating system's scheduler. Okay. What we really need here is some kind of coordination to ensure that that doesn't happen. Okay. There are ways of coordinating between threads, which we'll see a little bit later when we talk about the Go language. But for right now, we'll just cross our fingers and hope it doesn't happen. Okay, so I'll run it a few times. And looks like we're getting lucky here. I would guess if I change the order that I start these threads. Okay, this is what we wanted to avoid. We have these two threads that are doing two separate things. Right? Each thread is executing one of these. But just because we start a thread first doesn't necessarily mean it's going to run first. That's where the coordination is actually required. But for Clojure, we won't talk too much about how to do that. Like I said, it'll come up again in our next programming language. So it's likely that if we're going to have multiple threads in our program, then we're going to want to share at least some of the data between the threads. And we can do this in a safe and controlled way using refs. Okay, so here's an example that uses a ref but also creates a couple threads. So we have this thing called shared number, which is a ref that initially has a value of 0. We have this function called add1. This is what each one of the threads is going to do. And inside add1 we have a doSync. We create a transaction, and we're going to alter shared num by passing the inc function to the ref. Right? So this should increase the value of shared number by 1. Okay, here's where I create the threads. So I'm going to take 10, and I'm going to use this repeatedly function. Repeatedly takes a function, right, that has no arguments and returns an infinite lazy sequence of calls to it. So I only want this to happen 10 times, and what I want to do basically is create a new thread with the add1 function being the main body of the thread. Okay, so the threads is going to hold all of those thread objects. Now I'm going to iterate through using the doSeek. Okay, so this is kind of like a for loop where for each thread in the threads we can call a method. Okay, so I'm going to call the start method on each thread. Okay, and then afterwards, what I'm expecting to see is that the shared number, since it started at 0, I'm hoping that it has a final value of 10, which it does. So if we had not used software transactional memory in this case, if we had these 10 threads that are just trying to share that one piece of data, many things could have gone wrong. Okay, it would be possible for some of the threads to execute at exactly the same time on one of my many cores on my computer, and we may have lost one of those values. So think about the ATM example where it is actually possible to lose one of the transactions if two things happen at exactly the same time. Now it's a little bit hard to prove this to you because Clojure does such a good job of not even letting that happen. Okay, so most data is immutable and is therefore safe from concurrent updates. And all mutations of state must happen, if we are going to mutate state, like we're doing here, all of that must happen within a transaction, which guarantees that other threads will be blocked from interfering. Okay, so as I said before, this is a big and important topic. And you're just going to have to trust me for now that Clojure does a really good job of dealing with mutable state. If you ever take an operating systems course or a concurrent programming course, you're going to learn more about this topic and hopefully come to appreciate Clojure's STM even more.